Virtual model development of a single-phase induction machine. Single-phase induction motors are widely used in applications, and they excel in its simplicity, undemandingness, and reliability. They are also affordably priced. Usually, they are of smaller powers, approximate in the range of tens of watts to kilowatts units, and typically they are used in household appliances, because usually the single-phase supply system is available in the home distribution of electrical energy. The mechanical construction of the single-phase induction motor does not differ much from the three-phase one. Different is the way arrangement of the stator winding and supply. One winding in the stator of the single-phase induction motor cannot create rotating magnetic field necessary for running the machine, but it produces only a vibrant field. The rotor will not start without any auxiliary winding. This is why the motor has two stator windings, the main and the auxiliary ones. The motor power is transmitted through the main winding, which is stored in 2/3 of the stator slots and is supplied directly from the single-phase network. The auxiliary winding is rated for lower current than the main winding. In interactivity having the main winding, its aim is to develop rotating magnetic field with the form approaching as the most to the circular shape. The single-phase induction motors are distinguished by the structure of the rotor motor with wound rotor and squirrel cage rotor. The cage motor is used only for small performances. To get the rotating magnetic field, the current in the auxiliary winding shall be displaced by 90 degrees from the current in the main winding. This is achieved by connecting an inductor or a capacitor in series with the auxiliary winding and parallel connection of the circuit to the main winding connected to the supply. For this reason, a suitable reactance is connected into the auxiliary winding. Here we recognize the following. Starting with inductor, A, this is seldom used, it results in a lower efficiency starting with capacitor, B, connected full-time or by a double capacitor. Starting modes of one-phase induction machine. The capacitor CR connected into the auxiliary phase is optimally calculated according to the following equation. The one-phase induction motor is supplied by an alternating sinusoidal harmonic voltage that is generated by a simple harmonic oscillator in the model, having on its output the signal of harmonic voltage with the amplitude U1N and frequency F1 corresponding to the supply net. To achieve the starting torque, which is equal to the nominal, 2 to 3 times larger capacitor Cs is required, i.e. The motor mathematical model consists of models of electrical and mechanical parts. The electrical part is represented by the scheme in equivalent circuits, A, the main winding and, B, the auxiliary winding. Based on the equivalent circuits and dynamic equation of the motor, the mathematical equations with their representations are shown in Table 1. Mathematical and simulation models of subsystems of the one-phase induction machine. Combining all schemes together, we get the block diagram of the motor, which presents a core of the virtual model enabling deeper understanding of the phenomena in the motor at various modes of operation and supply. Simulink block diagram of one-phase induction motor. In investigating various modes of starting and operation, it is suitable to complete the model by supplementary blocks, like harmonic oscillator generating sinus and cosinus voltages, by the switches switching the capacitors according to the chose mode of operation, and by block generating the load torque in the optional time instant of loading the machine. The final scheme, used for the virtual model, is shown in the model of the motor with connected inputs and outputs enabling to simulate capacitor run and double capacitor starting the motor. The speed can be changed by the frequency, by changing the number of poles, and in a small scale by change of the voltage or value of the capacitor. The change of the direction of rotation is simply done by the pole change of the auxiliary winding. Time courses of the motor basic variables, motor torque, speed, and currents in both windings, are shown in simulation parameters. Time responses of the one-phase induction motor with a permanently connected capacitor in the stator reference frame, alpha, beta, at starting and loading the motor in the time 0.5 s, a, supply voltagesis alpha, s beta of the motor mode, b, motor torqueum, c, angular speed omega, d, static characteristic of the motor omega/m, and d stator currents, torque producing component is alpha and magnetic flow component is beta. To improve the motor performance during start period, a higher capacity is required in the auxiliary phase circuit. This is done by a capacitor Cs connected in parallel to the existing one, B, up to the time instant the motor runs by speed about 70% omega n, which is followed by a centrifugal switch. After disconnecting, only the capacitor CR of a lower value remains connected permanently. The next figure shows performance graphs of the motor with double capacitor. Simulation parameters: U1 equals 230 V, F1 equals 50 Hz, load equals 5 Nm, Cs equals 53 microfarads, CR equals 32 microfarads, omega n equals 110 rad/s, SEM equals 0.8 s, and T-load equals 0.5 s. Time response is of the one-phase induction motor with a double starting capacitor in the stator reference frame, alpha, beta, while starting and loading the motor at time 0.5 s, A, supply voltage Isis alpha, us beta of the motor mode, B, motor torque, C, angular speed omega, D, static characteristic of the motor omega equals Fm, E, F, stator currents, torque producing component is alpha and magnetic flow component is beta. To get the best motor performance, the constant stator flux must be preserved at various supply frequencies. From this condition, it follows up that U/F equals const. Time courses of the angular speed omega and motor torque at various frequencies of the supply voltage, a U equals 230 V, F equals 50 Hz, C'(S) equals 53 μ FCR equals 32 microfarads, BU equals 115 V, F equals 25 Hz, CSB equals 28 microfarads, CR equals 14 microfarads. After the verification of the mathematical model of the single-phase motor by simulation, we can design and develop the motor virtual model graphical user interface in the MATLAB program. The application is designed so that the user is granted simple handling in adjusting motor parameters, and waveforms show typical values of the motor. Graphical User Interface, GUI, allows you to visualize 4 different graphs: the input supply voltage, torque, angular velocity of the rotor, components of stator and rotor currents, and components of magnetic fluxes motor when starting the motor, during steady-state operation, and after loading at the chosen time. The ergonomics of handling and pedagogical respect should be strictly taken into consideration, as widely analyzed in the previous publications. Moreover, these aspects of using the model should be also considered. They should be suitable. For explanation, it lectures the phenomena and motor behavior during various operating modes and for preparation of the students for the experimentation in the labs. The developed GUI for the one-phase induction motor consists of 2 screens. The first, auxiliary, screen, serves. For explanation, it displays equivalent diagram of the motor on the left side and its mathematical model on the right side. The basic differential equations describing the motor that are in boxes, the color of which corresponds to the color of the graphs. For inputting the motor basic parameters. The second, main, screen, shows the graphs of the motor variables and contains control elements for simulation models and displaying the graphs. The screen for inputting parameters for the model of single-phase motor displaying motor equivalent diagram, equations of the model, and input motor parameters. The panel motor parameters A, enable to input motor parameters and thus to verify and compare behavior of various motors. After pushing the return button, the main program starts model simulation with the actual parameters. In the bottom right corner, there are 3 buttons. The model button displays the motor model in the Simulink program, as shown in, and inside the block of the motor, the full scheme appears according to the default button sets the preset values of the parameters, and the return button causes return to the second screen with the graphs, and immediately, the simulation starts with the set parameters. The GUI main screen with the graphs and control modes of calculation and visualization. A, the panel for input and changes basic parameters of the motor. B, the panel for calculation of value of the capacitor connected into the auxiliary phase. The panel coordinate system A, contains 3 switches to choose the supply mode: 1, supply by the harmonic voltage in the alpha, beta, coordinate system connected with the stator, 2, supply with a permanently connected capacitor, and 3, supply with the double capacitor. The panel graphs B, consist of 2 parts. The upper one contains 4 buttons serving to choose the graphs to display stator/rotor currents or stator/rotor magnetic fluxes. By the buttons in the lower part, The time graphs, I equals F1t, psi equals F2t, or mutual dependence of the variables is chosen, I alpha equals G1 I beta, psi alpha equals G1 psi beta. The variables of the motor we are intend to display, stator or rotor, are selected by the above-mentioned buttons.